Good morning, everyone. Thank you for being here.
Imagine you've trained an AI model to recognize objects in images like cats, dogs, and cars. Now, you want it to learn a new class, say, giraffes, but you only have a few examples.
This is the challenging scenario of incremental few-shot semantic segmentation, IFSS.
A major hurdle in this field is a classic dilemma. When we teach the model these new classes, it tends to forget what it learned before, a problem known as catastrophic forgetting. At the same time, it often overfits to the limited new data, failing to generalize. So, the core question of our work is, how can we enable a model to continuously learn new classes from just a few examples, without compromising its performance on the old ones? In this paper, we introduce a novel and elegant solution, a prompt-based method with a visual prompt pool. Instead of fine-tuning the entire model and risking interference, we design 3 levels of prompts to act as a dynamic knowledge library. 1. Task-persistent prompts to capture general knowledge, like what a foreground object typically looks like.
2. State-specific prompts to adapt to the unique needs of each learning phase.
3. And region-unique prompts to preserve fine-grained, local details like edges and textures. Crucially, we have a smart switching mechanism that activates only the necessary prompts for a given input.
This not only prevents knowledge interference but also makes the process highly efficient. The results are striking.
Our method achieves a new state-of-the-art, outperforming previous best methods by a significant margin, over 30% on one standard benchmark and nearly 14% on another. Today, I will walk you through the design of our prompt pool, explain how our adaptive switching mechanism works, and show you how this approach effectively tackles both catastrophic forgetting and overfitting. As we've seen, the key challenge is to integrate new classes seamlessly without disrupting old knowledge.
Our solution is a novel dense prediction framework based on multi-level, switchable prompts.
The core idea here is to use well-structured text semantics as a guiding signal to align visual and textual features, which allows new and old classes to coexist harmoniously in the same feature space.
Our framework tackles this through 3 key innovations. First, we predefine multiple background semantics. Instead of treating the background as a single, ambiguous category, we give it more precise definitions. This helps the model construct much clearer boundaries for background features in the feature space, which directly reduces the overlap and confusion between foreground objects and the background. Second, we designed a specialized component called the Focus Decomposition Decoder. This decoder contains 2 separate branches, think of them as 2 specialists.
One separator focuses solely on aligning text embeddings with foreground pixel features, while the other specializes in aligning them with background features. This dedicated processing ensures that the model pays precise attention to where it matters most for each category. Finally, and crucially, is how we use visual prompts. We keep the pre-trained visual encoder frozen to preserve foundational knowledge. To adapt to new classes, we don't fine-tune the entire model. Instead, we insert and update lightweight visual prompts within this frozen encoder. As we encounter new classes, we simply expand the model by adding new prompts.
This elegant design achieves 2 main benefits.
1. It allows the model to process the salient features of novel classes separately, preventing them from being overwhelmed by existing data. 2. It enables the model to dynamically adapt to background changes during incremental learning. Together, these mechanisms effectively alleviate the critical issue of confusion between novel classes and the background, setting the stage for robust and forget-free learning. Now that we understand the overall framework, let's look at the core innovation that makes it all work, our multi-level switchable prompts, or MSVP for short.
We started by identifying key limitations in existing visual prompt methods for segmentation.
1. They often lack fine-grained contextual information. 2. Their computational cost grows as more prompts are added. 3. And most critically, new prompts can interfere with old ones, leading to catastrophic forgetting. To overcome these challenges, we designed MSVP, a hierarchical prompting strategy that expertly balances knowledge retention and adaptability. It operates at 3 distinct levels of granularity. First,
the task-persistent prompts. Think of these as the foundation. They capture general, transferable knowledge like the fundamental concept of what separates a foreground object from the background. After the initial base training, these prompts are frozen, ensuring that this core understanding is never disrupted by learning new tasks. Second, the stage-specific prompts. These act as the specialists. They adapt to the unique requirements of each incremental learning stage, capturing discriminative knowledge like shape differences. They are initialized in the base stage and expanded for new classes, effectively transferring past experience to new tasks and striking a crucial balance between rigidity and plasticity. Third, the region-unique prompts. These are our fine detail artists. They encode category-specific structural information, such as edges and textures, to ensure the recovery of precise local details. This level is key for enhancing the model's ability to segment objects with high accuracy. Together, these three prompt levels enable comprehensive multi-granularity knowledge transfer across all stages of learning. But we didn't stop there. To truly mitigate interference and control computation, we introduced a smart prompt switching mechanism. This mechanism dynamically selects only the necessary prompts for a given input image. Here's how it works. We use a pre-trained model like DINOV2 as a query function. The global features from this query are used to attentively aggregate the most relevant stage-specific prompts. Meanwhile, the local features perform a nearest neighbor matching to select the most appropriate region-unique prompts. The result is a system that alleviates interference between prompts from different stages and, crucially, keeps the number of active prompts constant. This directly tackles the two major pitfalls we set out to avoid: catastrophic forgetting and escalating computational costs. During base training, all prompts and the decoder are trained. During incremental training, task-persistent prompts, stage-specific prompts of previous stages and region-unique prompts of old classes remain frozen. We expand stage-specific prompts to learn knowledge of new stages and expand region-unique prompts to learn local details of new classes, and exclusively train the newly expanded components. Now, let's look at the experimental results that validate our approach. We conducted comprehensive few-shot experiments under 1-shot, 2-shot, and 5-shot settings. The results are clear and compelling. First, on the core challenge of learning novel classes, our method sets a new state of the art. We achieve remarkable MIOU scores of 49.08% for 1-shot, 52.19% for 2-shot, and 58.13% for 5-shot. This consistent and high performance demonstrates our method's powerful capability to learn effectively from very few examples. Second, considering the overall performance, which balances both base and novel classes, our method also ranks first. This is measured by the harmonic mean score, where we achieve the best results of 58.71%, 60.93%, and 64.86% across the three settings. This is a critical point. It shows that our success in learning new classes does not come at the expense of forgetting the old ones. To provide context, let's compare with other types of methods. FSC methods are good at retaining base knowledge, as they use class prototypes that avoid corrupting what was already learned. However, FSS and IL methods struggle in this incremental few-shot setting. FSS methods forget old knowledge, while IL methods simply need more data than a few shots can provide. This brings us to the most striking comparison. When directly compared to the previous state-of-the-art IFSS method, SRAA, our method demonstrates a massive performance leap. We outperform SRAA on novel classes by a staggering margin. Plus 30.28% in the 1-shot scenario. Plus 25.79% in the 2-shot scenario. And plus 29.43% in the 5-shot scenario. Such a significant improvement, especially in the most challenging 1-shot setting, strongly confirms that our multi-level prompt framework effectively solves the core problems of catastrophic forgetting and overfitting that have plagued previous approaches. Beyond the numbers, let's look at some qualitative results to see what our model actually provides: a step-by-step visualization of our segmentation results for novel classes. These visualizations tell a very compelling story in two parts. First, they provide direct visual proof of our method's resistance to catastrophic forgetting.
As you can see in the examples, even after the model has gone through multiple rounds of learning new classes, it continues to correctly identify and segment the old classes with high accuracy.
There is no significant performance drop or confusion.
This visually confirms that our prompt-based strategy, especially the frozen task persistent prompts, successfully shields the foundational knowledge from being disrupted.
Second, the figures highlight our model's powerful few-shot generalization ability.
From just a single example of a novel class in this challenging one-shot setting, our model learns a robust representation. It can then accurately segment that same novel class in other, previously unseen test images.
The boundaries are clear, and the predictions are confident. Taken together, these visual results serve as a powerful and intuitive validation of our entire approach. They move beyond abstract metrics and show you directly that our prompt-based IFSS method is not just optimizing a number on a leaderboard, but is truly achieving the core goal, building a model that can continuously learn from a few examples without erasing what it already knows. This effectively bridges the gap between our quantitative scores and the model's practical capability.